So in this problem, we have a runaway truck with failed brakes. It is moving downgrade at 130 kilometers per hour. Just before the driver steers the truck up a frictionless emergency escape ramp with an inclination of theta equals 15 degrees. So the escape ramp has an inclination of 15 degrees. The truck's mass is 1.2 times 10 power 4 kilograms. What minimum length L must the ramp have if the truck is to stop momentarily along it? Assume that the truck is a particle. Justify this assumption. So we're looking for the minimum length of this ramp such that the truck would like stop at its end. So I'll name this point F, and I want the speed at F to be 0, and I'm looking for the length, and that is actually the distance covered at F, if anything. That's what we want. We're given the speed of the truck just before the driver steers the truck up the incline. So actually we have the speed which is here. I'll name this point I, and VI is 130 kilometers per hour. One hint I want to give you, whenever you are given a speed and asked for a position, speed and position are always linked through energy study. In forces, usually you would have something different. You would have, let's say, if you're asked about a speed and given forces, maybe think acceleration and then solve for the speed. So I'll do some energy conservation. I'll say E initial equals E final. The escape ramp is frictionless. That's why I said the energy is conserved. If there was friction, I will have to say E initial equals E final plus whatever we lost due to friction, or I will have to say delta E mechanical equals the work done by friction. Okay, so let's look at our initial point. Before I start substituting Ki and Ui, to substitute U, which is the potential energy, first let's look at what kind of potential energy we have here. We don't have a spring, we have gravity, we have gravitational potential energy because the height of the truck is changing. So that's how I decide what kind of potential energy I have. And when we want to work with gravitational potential energy, we have to select a reference to our height as usual. So I'm gonna choose my reference to be at the initial point because I just have these 2 points that I'm studying. Just point I and F. The lower one between them is I, so I'll take point I to be the point of 0 height. So the height here is 0, then there's no potential energy. At the final point, the speed is 0, as you saw before. So I'll take Kf to be 0. This goes away. I'll get equals U final. So half m V initial squared equals mg h final. The masses cancel out. I will solve for the height. H final will be V initial squared over 2g. You can substitute that. The speed is 130 kilometers per hour. Make sure you convert that to meters per second. How do we do this conversion? I will divide by 3.6. Always remember kilometer per hour to meters per second. Divide by 3.6. I will square that. And here I have 2 times 9.8. Can calculate this. you should get 66.5 meters. Now, be careful. We're not done with this part yet. Why? Because the question actually asks us for the length of the ramp. What we found was this. But what we want is this distance up the ramp. We can easily link them though through the angle theta that we have here. Namely, HF is the opposite to theta and L is the hypotenuse. So I'll take sine theta equals opposite over hypotenuse, which is going to be HF over L. What I want is L, so L will be HF over sine theta, which is 66.5 meters divided by sine 15. I will solve this. You will get 257 meters. This is the length of the ramp itself. So here, part A is solved. Let's look at part B. So in part B, we're asked about what happens to this length L. Would it increase, decrease, or remain the same if the truck's mass is decreased? So M decreases, what would happen to L? So I want you to take a look at our expression. I want to remind you how the mass canceled out everywhere all the way from the beginning. So the height depended on the initial speed only and the gravity. And later on, the length of the ramp itself depended on the height and the angle. So these are our factors. If the mass decreases, there will be no effect. In part C, we were asked if the speed is decreased. So here the initial decreases. Well, that's a different story because as you saw here, HF, we found it to be equal to V initial squared over 2G. And now V initial has decreased, then HF will decrease. Let's look at L. This is HF over sine 15, so it will also decrease. So yes, if V initial decreases, the length L decreases as well. Namely, let's say I asked you, let's put an extra part D. Let's say I asked you what happens to L if VI is reduced by half. Like I give you an exact value and I want an exact value. How I would write it is like this. I would say VI prime is half VI. Then I'll check what I calculated before. We found HF and then deduced L from it. So we wrote L to be HF over sine theta. And HF was VI squared over 2G. So that's the total formula for L. L prime will be HF prime, the angle theta is still the same, and HF prime will be VI prime squared over 2G. Now, VI prime is VI over 2, so I'll just substitute this here. I'll say this is VI over 2 all squared over 2G sine theta. So this will be VI squared over 4, like this 2 squared becomes 4, and I'll put it in the denominator, times 2G sine theta. This quantity is L that I solved for before. This is what I found before to calculate L. So I got L over 4. So if you reduce the speed by half, L reduces by 4. In this question, we have a pendulum of length L equals to 5 meters. Its bob, which effectively has all the mass, has a speed v0 when the cord makes an angle theta 0 equals 40 with the vertical. What is the speed of the bob when it is in its slowest position if v0 is 8 meters per second? So, okay, we're told the speed v0 is at a specific angle. So I'll start by just writing down the given clearly. V0 equals 8 meters per second when theta equals 40 degrees. The length L is 1.25 meters. We want the speed in the lowest position. This is basically V at lowest height. That's what we want. It's the speed here, by the way. It is basically the speed at this point. Let's name this point B and this point A. And point A is when the angle theta is 40. Oh, actually, let's name it O because like we labeled it as V0 already, so let's stick to that. So one thing we want is the speed at this point, which I labeled as B. You can see here the bob changes in height, so I expect to have some gravitational potential energy when I study conservation of energy. And that's how I'm approaching the problem as usual. I'll take UO plus KO equals UB plus KB. There's no friction here, the ball is hanging in air, so I can just take conservation of energy directly. When I want to work with the gravitational potential energy, as usual, I will start with a reference to the height. I'll take this to be my reference, so H at O is 0, which means U at O is 0. Oh, actually, this is U at B. Sorry about that. Let me fix it. So I always like to take the lowest point to be the point where my height is 0. So this is going to be 0. At point O, be careful. The speed is not 0, and the height is also not 0. So I have some height here. So these two terms will both stay here, and KB is what I want. I want the speed here. If I try to solve for KB, it will be UO plus KO, which is MGHO plus half M VO squared. I want VB, if anything, then the masses will cancel out. I'll get VB squared equals 2GHO plus VO squared. Looks good. What I still need is the height at O. I know the speed, it is 8 meters per second, here it is, but I don't really know the height at O, but I can solve for it. I know the length L, I know the angle theta. What I will do is similar to problem 8, which we solved before. I will take this right triangle. I'll mark it in red so you can see clearly which triangle I'm talking about. I'll take this triangle. In this triangle, I will solve for this length, which I will name D. And this quantity here is the same as here, which is HO. And the sum of D and HO is the pendulum itself. So one thing I know, D plus HO is the length of the pendulum. And D can be found from cosine theta 0, which is adjacent over hypotenuse. The adjacent side is D, the hypotenuse is L, so D is L cosine theta 0. So I can write in this equation, it becomes L cosine theta 0 plus H0 equals L. So H0 is L minus L cosine theta 0. We did this previously in another problem. It is common whenever you see a pendulum question and you're given the angle and you want to find the height of the pendulum, that's the way to go. So I'll find the height of the pendulum from the angle. L is 1.25 and theta 0 is 40. So I will solve here. I'll get 0.3 meters. And now I'll just substitute this in VB squared or VB. It will be radical 2 times 9.8 times HO, which is 0.3, plus V0, which is 8. If you solve this, you will find VB, it will be, let me check. Let me see, I might have something missing. Let's just double check everything. No, all looks good. All right, you will get 4.33 meters per second, actually 8.35. So in part B, what is the least value that V0 can have if the pendulum is to swing down and then up to a horizontal position, and in C to a vertical position with the cord remaining straight? So, okay, that's very interesting. We want an initial speed starting at angle 40 as before, but giving a different initial speed. So I want to change V0, which is 8, such that the pendulum reaches a horizontal position. It will swing down and go all the way up to a fully horizontal position. That's what we want. So I'll make a small sketch for that. I'll have the pendulum starting here with angle 40 and ending all the way here in the horizontal position. That's what I'm looking for. So I'll name this point O and I'll name this point F. I'll set EO to be equal to EF. I'll keep my height reference the same, which is here. This is H equals 0. HO is the same as the previous part because the angle is the same. So, and the height depends only on the length of the pendulum and the angle, and these are still the same. So this is 0.3 meters. My only issue is with the final point that I'm studying. So E at O, the energy at O will be K at O plus U at O, and E final will be, okay, let's look at our final point. Our final point definitely has a big height. So we have some potential energy. Our final point will not have any kinetic energy because we want the minimum length or the minimum size of VO so that the pendulum can reach this point. So I will make it barely reach this point. So it will not have any speed. That would need more initial speed, and we want the minimum initial speed for reaching this point. So there is no kinetic energy. I'll look at what I have. KO is what I want. I want the speed. So this is what I want. The height, we have it, 0.3. And the final potential energy will be mg times the height here. This whole height, which is actually just the length of the pendulum, right? So this height here is none other but the height of the pendulum. HF equals the length of the pendulum. Why? The pendulum, when it's vertical like that, the length here is L. It goes all the way to the highest point. It goes all the way here. Its height to the lowest point is still, it's like L, all right? So things look solvable. The mass cancels out. VO is gonna be GL minus G times 0.3. Well, I can substitute L and G as well. I'll do it in a minute. Times 2 with a radical. This will look like that. 2 into 9.8 into L is 1.25 minus 0.3 equals so this will be 4.33 meters per second. In part C, we want, well, things are harder in part C. We actually want the cord to reach the vertical height. So it should go all the way up. Let me just add an empty slide. So I'll make a sketch for part C as well. Again, the pendulum starts making an angle 40, and it will have to end all the way up. I'll actually repeat it. I'll redraw because I'll need some space on top. That's where the pendulum starts. The angle is 40, and it will go all the way up here. So this is point O, and this is point F. I'll keep my reference to be the same. It's over here. This is where the height is 0. So again, H at O is still the same, which was 0.3 meters. Let's look at HF. HF is none other but twice the length of the pendulum. VF is 0. I want the pendulum to barely make it to this maximum height. And V0 is what we want, or VO. So I'll do exactly the same study. I'll put KO plus UO equals KF plus UF. What we want is the speed, the initial speed to be for the pendulum to make it to this final point. So what I want is over here in the initial kinetic energy. I'll substitute everything and isolate the initial speed. So V final is 0, this goes away. The masses cancel out as before, and VO will be G into H final minus H initial times 2 with a radical. This is radical 2 times 9.8 times the final height is twice the length. This is 2 times 1.25. The initial height is 0.3. So I will solve for the speed. This will be 7.5 meters. In part D, we have a conceptual question. Do the answers to part B and C increase, decrease, or remain the same if theta 0 is increased by a few degrees? So I increased theta 0. I want to see what happens to the answers of B and C. What was the question in parts B and C? We were asked about the least value that V0 can have. So we want to see what happens to the initial needed speed if we increase the angle. Now, there are two ways to think of a solution to this question. The first is by physics. Physics-wise, if you look at the angle theta 0, if we increase it, then the potential energy increases, because when you increase the angle, you're essentially changing the height. That's all. If the potential energy increases, then the total energy increases, and we need less energy, less speed, less initial speed to reach the required heights of parts B and C. So if the angle is higher, we have some additional potential energy. We will need less kinetic energy, because now the total energy is always the sum of U and K. If U increases, I will need less kinetic energy to reach a certain height. That's the physics. Think about it using some math. So I remind you, what was our formula for V0? It was radical 2G into H final minus HO. And HO is the one that had the angle theta embedded in it. Namely, we had radical 2G into H final minus L into 1 minus cosine theta 0. This is where we saw the angle. If you expand, there will be a plus sign. You decrease theta 0, then V0 decreases. Let me show you again the expanded form. This is 2G into HF minus L plus L cosine theta 0. So if theta 0 okay, let me take a look again. The math doesn't seem to be matching. I'll double check the formula I got. Yeah, H0 is L into 1 minus cosine. Yeah, so if theta 0 increases, V0 would increase, and then I will need less V0 to attain the same final height. Yeah. So math-wise, it's a bit tricky to see, but what I'm looking for is this final height. I will need less speed to reach the same final height if I increase theta 0. Does this make sense? So here we have a block with mass m equals 2 kilograms. It is placed against a string on a frictionless incline with angle theta equals 30 degrees. The block is not attached to the spring, so it might leave the spring. The spring has a spring constant 19.6 newtons per centimeters. It is compressed by 20 centimeters and then released. So we compress the spring to a maximum compression of 20 centimeters, then we release it. What is the elastic potential energy of the compressed spring? So we want U elastic in the spring when it is compressed, basically at the maximum compression. Now, the potential energy has this formula. I have K, it is 19.6 newtons per centimeter, and X is the compression, which is also given to us. It is 20 centimeters. So I'll multiply by 20 centimeters squared. Now, there's a small issue I have to be careful about here. My unit here is centimeters squared, and here I have per centimeter. One of these centimeters will cancel out, but the other will not. So I prefer we convert everything to meters so that my final answer for the energy is joules. So I'll do some conversions. This will be half times 19.6 Newton. From centimeter to meter, I will multiply by 10 power minus 2, but this is in the denominator. And here I have 20 centimeters. I'll also convert that to meters. And this is squared. So you can see how I'll end up with this. 20 squared times 10 power minus 2. I can solve. I'll get 39.2 joules. In part B, we want the change in the gravitational potential energy of the block Earth system as the block moves from the release point to its highest point on the incline. So we want to see how the potential energy is going to change. Let's make a quick sketch. I think things would look clear to you if you see a clear sketch. I'll show you initially how the spring looked like. Initially, the spring was not compressed. Maybe it looked something like this. It was just here. I placed a mass and compressed the spring. I compressed it by 20 centimeters. So basically, this is 20. Then I released it. And when I released it, essentially what happened was it will try to get back to its initial length. And once it gets back to its initial length, it will momentarily stop, maybe compress back again. So basically, if I want to look for the change in the gravitational potential energy of the system, the block is going to move to its highest point on the incline when it is not compressed anymore. This is the highest point. Here, the block maybe is still attached. It's still here. Highest point is attained when the spring is not compressed anymore. So it was at some maximum compression. It started pushing to retain its, to get back to its original or natural length, to its equilibrium length. Once it's back to its equilibrium length, the spring is relaxed, right? So I'm gonna make use of that. It's not compressed anymore, so X is 0 here. I'll name this X final. And I will look for the change in the potential energy. This is actually gonna be easy. Why? Because if you set E at the maximum compression to be equal to E at the maximum height, then I will have K, let's name this K0, plus U0. It will be equal to K final plus U final. Initially, the block did not have any initial speed. It was released from rest, so this was 0. Remember, what I'm looking for is the change in the gravitational potential energy. I want delta U, and delta U is none other but U final minus U initial, or U0, which I can see is right here. I'll take U final minus U0 to one side, and this will be equal to minus K final. So I just like isolated U final minus U0 because this is none other but delta U. So delta U will be minus K final. Hold on, I have something missing here, just a second. Okay, so there's something I missed here, which is I have two kinds of potential energy to account for, a gravitational potential energy and an elastic potential energy. So let's be aware of these, because one thing I just noticed, K final is actually 0. This is the highest point. At the highest point, V final is also 0. What's not 0 is H final, the height. So I'm gonna fix my formula here. In fact, I'll put two kinds of potential energies. That's how I'm gonna fix it. So here I have, at the maximum compression, I have some U elastic initial plus U gravitational initial. K final is also 0 because at the maximum height, the block is also with no speed. And U final is the final potential energy. It will be U elastic final plus U potential final. So notice how here I have an oblique spring. So I will have both gravitational and elastic potential energy. One thing I want you also to see is at the final point, X final is 0. The spring is not compressed. So this will be 0 as well. Now, what I want is the change in the potential energy. I'll name this UG, which is UG final minus UG initial. So what I want is UG final minus UGO, or initial. If you rearrange these from my equation, this will be minus U elastic initial. And U elastic initial, I found it in the previous part. It was 39.2 joules. Let me just double check everything in my signs. Okay, I have a plus sign here because I took this to this side and this is already plus, so it will stay plus. And that makes sense. Let's look at the physics here. The block has increased in height, so its gravitational potential energy should increase. So it makes sense for delta UG to be positive. So this is the change in the gravitational potential energy. It's none other but the initial elastic potential energy. So here what happened essentially is the elastic potential energy of the spring was all converted to gravitational potential energy. We still have one part C. We want how far along the incline is the highest point from the release point. So we want to just find how far along the incline. So we want to find this maximum distance D here that the block is gonna basically cover. So what I'm gonna find is I'll find the final height, because once I have the final height, I can link that to D simply by using sine 30. So to find the final height, I'll just work with the conservation of energy. I'll use E final equals E initial, and I'll substitute as before. Initially, I had just some elastic potential energy, and at the final point, okay, let's fix this. So the final point is at the right-hand side. At the right-hand side, I don't have any elastic potential energy, right? At the right-hand side, I just have mgh final. There's no kinetic energy. It's like at the maximum height, so the speed is 0. At the initial point, I only have half kx final x initial squared. Initially, the compression is 20 centimeters, so I can substitute that. I will solve for h final. This will be, let's see, half k xo squared over mg. Do we have k, the spring constant? Yes. Actually, I have this whole term here. I found it before. It was 39 from part A. It's 39.2. I'll just divide by mg to find the height. The height will be 2 meters. And then I will say, so I found h final, but what I want is the distance. I can find it by studying the angle. Sine 30 is h final over d, so d is h final over sine 30. So I'll divide 2 by sine 30. I will get 4 meters. This is the distance covered by the block as it moves up the incline.